floor. Right. So today we're finally going to get to the Weil Petersson metric. Maybe before I get started, let me just mention that I've put up the names of my 3 co-authors on this project up there. So let me start with by saying something about the Weil Petersson metric on Teicl space. It's been mentioned several times before. So S will be a surface. We'll have genus G, and I'm used to using N for the number of punctures, so I'll stick to that. And I think we want an inequality like 3 times G minus 1 plus N, I think greater than or equal to 1, to make sure that the surface will support metrics of negative curvature, of constant negative curvature. So the idea of Teicl, you have Teicl space, and you also have the moduli space. And these things both index structures on our surface. And there are 3 types of structure, at least, that are indexed. Maybe there are more. One is conformal structure. Another is complex structure. We've heard a lot, I think you've heard a lot about them in the course of the last 3 weeks, so I probably don't need to say really anything about those. And the third structure, which I'll say somewhat more about today, is hyperbolic structure. So hyperbolic metric on S. And the sort of hyperbolic metric that you're interested in should be complete, and it should have finite volume. The finite volume condition is relevant if you've got punctures on the surface. So it means that at each puncture, you have to have the familiar hyperbolic cusp. You're not allowed to have one of those funnel things. And so the idea is that these spaces index all possible structures of whichever type you care about. And they do it in slightly different ways. Oh, and I probably should have said that this surface is oriented. Right, so the moduli space is the set of all possible structures modulo the action of diffeomorphisms. And I'll put a plus sign up there to indicate that you want orientation preserving diffeomorphisms. I'm not interested in switching orientations. I don't think anyone is here. So well, you could pick your favorite type of structure and think of all possible structures of that type, and then quotient out by these actions. So the idea is that for any type of structure you think about, there's a ridiculous number of them, because you can take your structure, you can take a diffeomorphism, you can move the structure with the diffeomorphism, and well, you've got something new because you moved it. On the other hand, it's really the same. So it's very natural to quotient out by that action. And then the Teicl space is the same idea. Yes, yeah. And Teicl space is the same idea, but you're a little more selective about which diffeomorphisms you use. I'll put a subscript 0 there, which is meant to indicate that I look at the component of the identity in the diffeomorphism group. And this time I don't have to specify orientation preserving, because that will come for free if I stick in that component. And so this is obviously, this group is contained in the subgroup of that one. So you get a bigger space here. And of course, there is the mapping class group, which is diff plus mod diff 0. And so moduli space is Teicl space quotiented by the mapping class group. And so let me draw some pictures of sort of the simplest example. Possibly what I'm about to say is known to everyone here, but maybe it wouldn't hurt to say it anyway. So I want to think about G equals 1 and N equals 1. So I'm thinking of the puncture torus with one puncture. And I want to think about hyperbolic structures. So complete hyperbolic metrics on that. So this is going to turn into the cusp, and you're going to have hyperbolic geometry, well, everywhere. And so one way to think of these things about building them is that I should create myself a hyperbolic quadrilateral. And I actually want the angles in this quadrilateral to add up to, I think it's 2 pi, the same as they would in a Euclidean quadrilateral. This does not look very good in hyperbolic geometry, but sitting in the middle of this thing is the hyperbolic cusp. So if I have that set up, I can then identify opposite edges. And what you can see if you think of this, if you simplify this cusp down to just a single puncture, you can see that you're creating a once punctured torus. And so this angle, so if the angles are alpha and beta, you need alpha plus beta equals pi. And then these 4 corners fit together to give just a nice piece of hyperbolic plane. So you can build all of the different hyperbolic metrics arise from that construction. And what you can vary is the shape of this parallelogram. Obviously, the area of what you're looking at is fixed. I can't, there's some integral based on the Gauss-Bonnet formula that has to come out to whatever the right value is. So then I can think of I can then draw a picture of all the possible lattices I can draw. I can fix a base point. I can assume that, say this bottom side goes from 0 to 1, and then the other corner goes to z. So this is exactly the same picture as you would draw if you're talking about the Teicl space for flat metrics on the unpunctured torus. And so z should be thought of really as the ratio of the two sides, including the choice of angle. And then you have to scale the picture so that the area comes out right. But so this gives a picture of Teicl space, and you can see that you're getting the upper half plane, which is, I think, well known to everyone. And then if you now think about different lattices, instead of thinking about the one that I drew, if I looked at that one, I would be getting the same geometry. So the moduli space, well, the mapping class group in this case, is going to be the group that maps the lattice into itself. So this is the modular group. And the modular surface, the moduli space is the familiar modular surface. So in the upper half plane, you have the familiar fundamental domain, and you end up with a surface that has two cone points in it and a cusp. So there's a picture of mod 1, 1. And these two cone points correspond to special lattices that have extra symmetries. One of those lattices is based on the square. The other one really is based on the equilateral triangle. It's the quadrilateral formed by gluing two equilateral triangles together. So that's what you get in that case. And in general, you get the Teicl space as a complex dimension 3 times g minus 1 plus n. And so if you are a naive person and think about real dimension, the real dimension is 6g minus 6 plus 2n. And so when n and g are both 1, you get 1 here and 2 there, which is consistent with what I drew. And Teicl space is actually a complex, has a complex structure, which is then passed down to the moduli space. There is a complex structure. It's been described in lectures that I heard earlier this week. I think it's easier to see what the complex structure is if you think about varying the conformal or the complex structure on Teicl space. The idea is if you have some way of varying your complex structure, you can then take that way of varying it and just rotate it at each point, rotate what you're doing by 90 degrees. And that's the effect of multiplication by I on the tangent vector. So that's roughly where the complex structure comes from. So there is a complex structure. Okay, so I think now what I will do is remind you of the idea of Fenchel Nielson coordinates. So if I have, let me draw, say, a surface of genus 2, and then what I want to do is to chop it up into pairs of pants. So I think I can do that with 1, in this case I need 3 things. And the number of curves I have to draw to chop it up into pairs of pants is exactly this number. And it's not a coincidence. So once you've chopped it up into pairs of pants, you can then describe the hyperbolic geometry with a finite list of numbers. You just have, for each of the curves that you drew, you should think of these as the closed geodesics that are the boundaries of the pairs of pants. And to describe a pair of pants, all you need to know are the lengths of the 3 boundary pieces. They then uniquely determine the hyperbolic geometry in here. So if for each of my curves I write down the lengths, and then I'm not done with specifying what the geometry on the surface is, because I can make changes by doing Dane twists along these curves. I can cut along my closed geodesic, and then I can rotate one side relative to the other. And so you get some parameters, which are usually denoted by tau, 1 twist for each closed geodesic. Now, length is a completely natural, straightforward, well-defined parameter. Obviously, it takes positive real values. Twist can be any amount you like. You can twist forward or backwards as much as you wish. There is one oddity about twist, though. It's undefined. It's undefinable, in fact. because there is no canonical notion of what zero twist means. All you could do is start off with one reference picture and decree this is non-twisted, and then you can measure twist starting from here. But you could equally well take a different reference picture. So twist is determined only up to a constant. But that's really not a problem. It's no more of a problem than the indefinite integral being determined only up to a constant. All that you ever do with twist is do things like compare one twist to another. So you look at a difference, which is well defined, or you take a d of twist, which is well defined. So that's all right. So, and then you will notice that we have two real coordinates for each one of the curves, and that's where this real dimension comes from. And so now I think I can tell you what the Weil Petersson metric is. This is one description of it. So this is Wolpert's formula for the Weil Petersson metric. So Wolpert writes down a two-form. I take my decomposition, my set of curves that gave me Fenchel Nielson coordinates. For some reason, you put a half in front. Well, the half, I copied this from our paper, so hopefully this half is right. The only purpose of the half is to match this formula up with other formulas. And then you take a sum over all of those curves. So it'll be 3g minus 3 plus n. And then you take dli, which d tau I. That is a two-form. So the first thing you would think is, well, okay, great. I've got my Pants decomposition, I get my two-form. I take a different Pants decomposition, and there are infinitely many of them. So it looks like you've got an infinite class of two forms. Well, no. Part of what Wolpert proved is that this two-form is independent of the choice of pairs of Pants. You can imagine how that could come about, that things somehow sort of cancel each other out and you get the same thing whatever pair of Pants you take. But I gather that it is not obvious. So the fact that you get something independent of the pair of Pants decomposition says that this two-form must be something that matters. That's a sort of clear message that this two-form has to be something kind of natural. So it's independent of the choice of pairs of Pants. Right, so now you have a two-form. We also have a complex manifold. Oh, and this two-form is known to be closed and non-degenerate and good things like that, yes? Yeah? Oh, well, if I take the once-punctured torus, whoops, in this case, there's just one closed geodesic. And for my, the pair of Pants that you have here is degenerate. You have a length 0 at one end of it. And these two have to match because they're going to be glued together. So you've just got, in this case, you just get the one number, L1 and tau 1. So the pairs of Pants kind of, the cusp ends of the pairs of Pants just don't contribute any, you don't get any choice at those ends. The the choices come, so if I had a more elaborate surface, I could have a cusp and have another cusp and something there and a couple more cusps. And so then I think I did 1, 2, 3, help. Have I put in enough? I hope so. And then if you cut, so I think that's, yeah, so if you do that, there are pairs of pants that have cusps at the end. If I'd done it, I could even have had a pair of pants with 2 cusps. So if I had a sphere with 4 punctures, I'd get 1 waist there, and I'd have a pair of pants with 2 cusp ends, and the only choice is the length here. Same for this side. And then, given the length, you can then twist by as much as you like. But so the pairs of pants, well, the cusps just kind of disappear into the formalism. Does that help? Okay. So, yeah, so this formula is independent of the choice of pairs of pants. It is actually a closed, non-degenerate 2 form. The reason why it's closed is because it's actually exact. Yes? Well, the N appears there because the geodesics, once you've drawn them, all look kind of the same. They're sort of inside the interior of your hyperbolic geometry. It's just that each time you put in an extra cusp, you find that you need to put in 1 more geodesic to achieve your cutting into pairs of pants. And for each cusp, it's going to contribute an end to a pair of pants where the geodesic at the end has length 0, and it's actually the point at infinity. Yeah, so well, this number just gives the number of geodesics that you need to make the boundaries. So you know that some of the pairs of there'll be pairs of pants where all 3 ends of them are geodesics that you cut along. There could be other pairs of pants where 1 end is a cusp. There can be pairs of pants where you've got 2 cusp ends. You're not going to have a pair of pants with 3 cusp ends. Then you're talking about the ideal pair of pants. It does have a Teicl space. Nobody studies it very much because it consists of 1 point. And there's a feeling that we have complete understanding of that. Okay, so I have and so this 2 form is actually exact, and I'm not sure who first exhibited the 1 form that you differentiate. There's certainly there's a paper of McMullen which has a 1 form in it, and D of this 1 form gives the Weil Petersson form. Okay, well, can people still? Maybe I can make some space. I've probably got enough room. Let's make some space here. So I have the setup of a complex manifold, and I have a nice 2 form on it. So you can create what's called a Kahler metric. I've written Kahler with the 2 dots on the A. You also see it written as AE. The same with Teicl, either 2 dots on the U or UE. So what you do is, I want to define my Weil Petersson metric acting on 2 tangent vectors. What I do is I plug them into the 2 form, but I rotate one of them. So J squared is minus the identity This is the rotation produced by the complex structure. So that is one description of the Weil Petersson metric. One thing I should warn you about is that if you look at this formula, so the Fenchel Nielson coordinates make Teicl space look like r to this power times r plus to this power. And there seems like there's an obvious complex structure where you have well, there is an obvious complex structure. You've got Li and tau I, they define a plane, and you just do rotation, Euclidean rotation in that plane. That is a complex structure. It's not the one we're using here. Life is not like that. So this formula makes the form very visible. The complex structure is kind of hidden. Anyway, there is a description of the Weil Petersson metric. And so it's not the original description. So the way it came about, this was a theorem of Wolpert showing that the Weil Petersson metric as defined by Weil is given by this formula. I think IISER refers to this as Wolpert's magic formula. It's a really beautiful theorem. And so the original description, I will say just a little about. I will suppress some details. If you really want to read them, we describe it more fully in the introduction to our paper. So the original description, it's pretty easiest to talk about cotangent vectors to Teicl space rather than tangent vectors. And cotangent vectors are integrable meromorphic quadratic differentials with at most poles at the cusps. So they don't get to be terribly meromorphic. The only poles they're allowed to have are at the cusps. Oh, and I've left out the word simple. So they're somewhat restricted. And then if you have such a quadratic differential, it looks locally in complex coordinates like some polymorphic function times dz squared. And then you can think of defining norms on these guys. Basically, you do some norm on the function. You do some integral of some power of modulus of q. And so there's an L2 norm that you can think of. There's some kind of fudge factor that goes into the integral that I don't want to go near today. Now, the L2 norm here produces Weil Petersson. If you do the L1 norm, you get the Teicl metric. I think I've got that right. And then if you switch over to thinking about the tangent bundle, the corresponding things that you do are still L2 norm for Weil Petersson, and it becomes the L infinity norm to get the Teicl metric. And so seeing that this description matches up with Wolpert's description is what's in Wolpert's paper. It's also the final chapter of volume 1 of Hubbard's text on Teicl theory. So my idea today is to just tell you things about Teicl space. And if you really want to know about them, you either read the literature, or what I personally recommend is finding somebody who knows Teicl space, such as IISER, and listening to what they say. Okay, so we have one question that this raises, to which I do not know the answer, is obviously there are numbers in between 1 and 2. You could define a structure on Teicl space and moduli space by, I suppose there are also numbers between 2 and infinity. So there's a whole one parameter family of metrics that you could look at. These are the 2 that are studied. What about the other ones? My ignorance on this subject is total, but I also believe that my knowledge of these things is as much as anyone else's. There seems to be absolutely nothing known. And I would speculate that if you think of some number, say, p, between 1 and 2, I would guess that you would get something that behaves like one end or the other. And my guess is it would be like the Teicl end. This is just not known. It would seem like a question that's there to be, somebody ought to be capable of working something out. And I don't know enough about Teicl theory to know whether this is an insanely difficult project or if it's something that could be done, perhaps by one of you. It won't be done by me. So we have our metric, our Weil Petersson metric, and it has various properties, none of which I find obvious, but known to be true. So, properties of the Weil Petersson metric. By the way, I say Weil. Andre Weil. This is Andre Weil. All I know is he's French. If you really want to know how to pronounce Weil properly, you should ask someone like Francois Labrie. What is the proper way to pronounce Weil? Okay, so I'm not doing too badly, am I? Thank you. Right. To really talk about this subject, you should be French. So it turns out to be Ramanujan. I'm sure that this has something to do with the 2 that we used L2 norm. That's the only intuition I can offer there. It has negative sectional curvatures. If you want intuition about this, you could try asking Professor Wolf. He actually explained, what he explained to me was calculations that he knows how to do and that he has intuition about. I still don't have intuition. I've also been shown a paper that gives a description, yet another description of the Weil Petersson metric that has a vague resemblance to one of the models of hyperbolic space as some sort of hyperboloid of some kind. But then the more I looked at what was actually going on in the paper, the more it seemed to me that it wasn't quite like what I knew. And, it seemed to be suggestive rather than real intuition. And I think the history of this suggests that it's not entirely intuitive. Alfors did not prove this. He proved that you have negative holomorphic sectional curvatures. Perhaps that was because Alfors only cares about holomorphic things, I'm not sure. So holomorphic sectional curvatures means there are some, in a complex manifold, not all planes are equal. there are holomorphic planes, which I think are spanned by V and I times V. And then, so for those planes, he worked out the sectional curvature and showed it was negative. And the general result, I think there was work by Royden, Tromba, and Wolpert. So it is known that you have negative sectional curvatures. So great, we've got the kind of setup that I was talking about yesterday. Variable negative curvature. Oh, and there's more good news. The Weil Petersson volume of the moduli space is finite. Okay, we don't have compactness because of, you can see that cusp on the modular surface where you used to be able to. The picture has disappeared, but we at least have finite volume, so we're in with a chance. There might be some difficulties sort of because of the non-compactness. And in fact, there are rather considerable difficulties. So, no. So if you have the modular surface picture, there is a negative upper bound on the curvature. The sharp lower bound is minus infinity. If you move to a surface where you've got, more stuff going on, so the Teicl space is higher dimensional, the sharp bounds on the curvature are now minus infinity and 0. So it's just, that's the extent to which it's pinched. So yeah. Curvature not bounded. And derivatives of the curvature not bounded either. This is bad news. There's worse to come. Moduli space and Teicl space are not complete. So here's my cusp. If I hit my modular surface for the 1-1 case, if I use the Teicl metric, by some miracle, it turns out to actually be Ramanujan, but in higher dimensions, it's only Fenchel. And in this case, it turns out to be the hyperbolic metric, and you see the modular surface that Dani talked about in his lectures, and life is great. With the Weil Petersson metric, you see something different. If you look in the upper half plane, you have something like the inner product of the hyperbolic inner product of two vectors is the Euclidean inner product divided by, I'll use y for that coordinate, by y squared. For the Weil Petersson metric, you should think of changing y squared to y cubed. And this cusp is not exactly like that geometry, but it's asymptotic to it. The closer you get to the end of the cusp, the closer you are to that geometry. And this has a consequence that the cusp comes to an end at finite distance. So if you set off in the wrong direction, you get to the end of the world, and you get there in finite time. Yes. And while you are approaching the end of the world, the curvature around you is blowing up to or down to minus infinity. The derivative of the curvature is going crazy. It's not good. So this is somewhat bad for talking about the kind of things I want to talk about. There are also some cone points here which are mildly annoying. Maybe one more remark to make is that if I have a surface, say, like this one, if I shrink the geodesic in the middle down very, very short, you then have a very long neck on either side of it. And then it basically, the surface starts to look like two punctured tori. And then I can do Teicl stuff for this punctured torus kind of independently of stuff for this one. And so while this one's really short, Teicl space is starting to look more and more like Teicl 1-1 cross Teicl 1-1. And that's reflected in the Weil Petersson metric. It looks more and more like the product of the Weil Petersson metrics for those two guys. And product metrics have planes of zero curvature. If I take a vector in a geodesic in one factor and a geodesic in the other factor, the product of those geodesics gives you a copy of R2, which is immersed in the manifold, and it is totally geodesically and isometrically immersed. So you get zero curvature for the planes tangent to it. And so that's where the approach to zero curvature in the higher dimensional Teicl spaces comes from. So we know all of that. What other things? It's incomplete. Right, I think that more or less covers what we know. Now, Weil Petersson metric is good for something. And there's a reason, and what it's good for is thinking about how the hyperbolic geometry on your surface S varies. So there are nice relations between Weil Petersson geometry in Teicl space and hyperbolic geometry in on S. And if you were thinking of varying the complex structure, there are those pictures of the surfaces which are flat everywhere except for those cone-like singularities. If you're thinking of how those structures vary, then you want to think of the Teicl metric on Teicl space. But here we wanted to use the Weil Petersson metric, and the basic fact is that if L is the length, I'll say, of a closed geodesic in S, that isn't quite right. What I'm really saying is I've got a free homotopy class, and for each choice of hyperbolic metric in S, there is a unique closed geodesic in that class. And then I want to see how the length of that geodesic varies as we vary. So just think of it as one geodesic whose length changes as we change the metric. Then L and L to the 1/2 are both convex functions along Weil Petersson geodesics in Teicl space. I believe this is a result of Wolpert. I hope you're noticing that the name Wolpert keeps going up on the board. This is because there is no one in the world who knows more about Weil Petersson geometry than Scott Wolpert. And the work that we did would have been completely impossible without what he did. And so this is certainly a major building block in understanding Weil Petersson geometry. And also it's a very strong hint that it's the right geometry to think of if you're seeing how the hyperbolic structures on S are varying. And there are some beautiful results of Mirzakhani, which I think I haven't got time for. They're mentioned in the introduction to our paper. Okay, so we have that. So I think, so this is something good. So now we have a somewhat disastrous, oh yeah, there's one more thing I should mention. These cone points are a nuisance. I don't like them, and I'm going to get rid of them now. The way you get rid of them is you can pass to a finite covering of the sky, because these are cone points have the cone angle is, I think it's pi over 6 and pi over, I can't remember, it's 2 or 4 something, I'll say 4. Anyway, you can do the business of sort of the kind of thing that you can imagine. And what that corresponds to is looking at a certain subgroup of the mapping class group that has finite index. And then you can get rid of the cone, of these cone points. So really, we don't really think about moduli space. We think about a certain finite covering of it. And in any dimension, you can go up to a finite covering and abolish all of the cone-like stuff inside the interior. The only disaster that's left is the end of the world. So I will just talk about moduli space, but really I'm talking about a finite covering of it. Henceforth I just talk about moduli space. Right. So now I think we start moving to things that are a little bit positive. So the first thing is that for almost, so mu is again the Livoulle measure on, it's either T1 Teicl or T1 mod. And of course the mapping class, well, the projection preserves this metric. So the metric here is invariant under the action of the mapping class group. So the first good piece of news is that for mu, almost every V in T1 of the moduli space, the geodesic gamma sub V of T is defined for all T in R. So at least there's something to talk about. And the proof of this is due to Wolpert. And the idea of the proof is that if you look at a neighborhood of infinity, sort of out here, if you get really close to infinity, there's very, very little volume out here. And then if I think about a small neighborhood of infinity and a large time, and I flow this neighborhood of infinity around, it's so small that even after I've flowed it forward and backwards for 1 million years, I still have very little volume. And so just by some rather naive estimates on what somebody like Wolpert has to play with the estimate that there's very little volume at infinity. But once you have that, you can show that almost every geodesic fails to get to infinity. Because the set of geodesics that get very close to infinity in some given time has very small volume. So there's a fairly simple argument that shows that this is true. The next thing that's good is another, so these are all results of Wolpert. The next thing that's good is what's called geodesic convexity in Teicl space. So if I have a metric that is not complete, there are some bad things that can happen. I think about the disk, and then think about removing the center of the disk. And then if I want to try to go from A to B, I can't, because the hole is in the way. This is not good. So Teicl space with Weil Petersson metric, whatever its drawbacks, it does not look like that. The incompleteness is because you can get to there in finite time. And if I have 2 points, and when you lift, you still have even in Teicl space, you have the issue that you can go out to the boundary and get there in finite time. But if I have 2 points inside Teicl space, so if P and Q are in Teicl space, there is a Weil Petersson geodesic joining them. So as long as I try start and end in Teicl space, I can do it. And then there'll be a unique geodesic. And so this, once you have this observation, this allows construction of horospheres. So we can then build the sort of the same kind of stable and unstable manifolds that I talked about yesterday. So you've got most of the picture that we had yesterday. You can also, you get exponential, you get the exponential expansion of most Jacobi fields and some exponential contraction. And I'll just describe that loosely. So your typical, we have, if we think of moduli space, the unit tangent bundle has finite volume. So the Poincare recurrence theorem says that if I start somewhere, or for almost every vector, we'll pick one whose geodesic goes on forever. So it's got an orbit under the geodesic flow, and this orbit keeps coming back close to where it began, and it comes back with positive frequency. And then if you move a little bit along the orbit in negative curvature, you get a certain amount of expansion of the Jacobi fields that ought to be growing. And then you go off somewhere and you don't know what happens. Well, you know something about what happens. You know that things don't shrink. And then you come back and then things grow again. And then they don't shrink. And you come back and they grow. And you're coming back and getting this growth with positive frequency. And then it's easy to make an estimate to show that you're getting exponential growth of things. So you get the kind of hyperbolic behavior that we had last time. The only difference is it may not be uniform. In the case of this guy, it will be uniform because there is a negative upper bound on the curvature. But in the higher dimensional spaces where you've got some zero or curvature that's almost zero, while you're away doing stuff, you might be spending time on the zero curvature and things could slow down there. So you've got most of the ingredients that give you hope that good things ought to be true. So I think now I will state the results. Let's see, there were some early results by, I think, Wolpert. And then I can't remember who wrote the general paper. It might be Maser, and others, I will say. They showed that the Weil Petersson geodesic flow is topologically I'll say has a dense orbit. So that's good. And this actually provoked the work that we did because I think Wolpert was giving a talk about this result and he was asked, well, do we know that it's ergodic? And it's got negative curvature and all. Don't we know that it's ergodic? And Wolpert said, well, no, we don't. And the questioner then said, well, gosh, it's kind of pathetic that we don't know that this geodesic flow with negative curvature is ergodic. And so Maser came home from that meeting and said to Amy Wilkinson, I don't want to be pathetic. We've got to do this. So in the end, we did it. So there is, I wrote a coding of the authors. So this is BM1W. And in this paper, we prove that the Weil Petersson geodesic flow is ergodic. This is on T1 Okay, it's not really on T1 of moduli space, it's on T1 of that finite cover. But it is ergodic with respect to Livoulle measure. And for those who care about such things, well, I will write the word mixing. And for people who care about such things, it also has the Bernoulli property, which is a yet stronger version of mixing. So what mixing means is that if I have two subsets of positive measure, after a while, stuff from one of the sets should have moved into the other set. And the amount of this set that's in the other set should tend to the right thing. So I want mixing, it means something like if A and B, if I have mu of A positive, mu of B positive, if I look at the measure of phi T of A intersect B, this should converge to mu, and I'll assume that mu of the whole space is 1. Otherwise, there'll be some scaling factors which I will get wrong. This should converge to mu of A times mu of B. That's what mixing says. And then you can ask how fast this this convergence happens. It could be exponential, in which case you have exponential mixing. It could be only polynomial, in which case you have polynomial mixing. And so there are two papers by the four of us. One paper shows that if the real dimension of Teicl space is greater than or equal to 4, then the rate of mixing is at most polynomial. I think of degree 10, some number. And we don't know that it's that fast. It should be somehow, but all we know is that it's no better. And the reason for it has got to do with those planes of nearly zero curvature. Zero curvature does not promote. Mixing tends to come about from divergence of things, and zero curvature is not very good at producing divergence. And the other result is that for the 1,1 case and also the 0,4 cases, this is when the Teicl space has real dimension 2, you do get exponential mixing. So those are the results. This paper is published, it's actually in Annals. These two are on the archive. And so, yeah, I've left myself about 10 minutes to say something about what we do. So if you look at these papers, let's see, this one is pretty long. There's a lot of technical stuff in it. This one is pleasantly short. This one, for the exponential mixing, is unpleasantly long. And there's some truly awful technical stuff which we actually put in some kind of appendix that's available online. So I'm going to skip all of the ghastly calculations and try to say something about why it all ought to work. And so the real problem is, well, it all comes down to proving absolute continuity of the stable and unstable foliations. The same thing that Anosov proved in the case of variable negative curvature. And you cannot directly use Anosov's proof, because hidden in the arguments I showed yesterday, there are some uniform estimates on things, and we don't have uniform estimates here. So there is a book by Katok and Stelegn, and the nature of what the result in the book is that you can still prove absolute continuity of the stable and unstable foliations. If the blow-up of, I'll just say, well, of, I'll say irrelevant quantities as we approach the boundary, this blow-up should be controlled. And what I mean by controlled is if Q of X is some sort of quantity, and the main candidates that we're interested in are the curvature, derivative of the curvature, or maybe some component of these things, and then you have some notion of the size of it, the appropriate notion, and this should be less than or equal to constant times the distance from X to the boundary of, let's say, T1 modular space. And then this should be to some power, some negative power. So if you have exponential blow up as you go out to the boundary, forget it. But if it's controlled like that, then you're in business. And so what we did in this paper was Wolpert already had an estimate on the curvature. We supplied an estimate on the derivative of the curvature. And then you also have to control, as well as these things, you have to control the derivative of the time one map. And there's a ghastly section where we acquire that control. Now, that's roughly what we did in that paper. And then there has been progress since we wrote that paper. One of the things in mathematics is that once you know that something must be possible, you can then do it. So I think probably the biggest feature of this paper is we actually did something that Wolpert had not yet done. And so, because once Wolpert knows that we can do it, well, now Wolpert can do things. So now there is a paper by Wolpert and so we got estimates of this nature. Wolpert now has the right estimates. On curvature and its derivatives. And so if I take the curvature, let's take R for the curvature tensor, and I differentiate K times and look at the size of some component. This is less than or equal to, well, constant times distance, this is at some place, maybe at V, distance from V to the boundary of T1, moduli space. The relevant power is minus 2 plus K. I hope I've got the right power. Anyway, there is an appropriate power, and it goes up by 1 each time you differentiate. And I hope I've remembered, I think minus 2 is what I want in the base case of the curvature, which is what we already knew when we wrote the initial paper. and we used that all over in that paper. So, you know, the punchline at the end of the talk is, what does this really tell you? So, suppose I have, if I have, so let's think of our modular. So we're out here near the cusp. We're at distance d from the cusp. What I want to do is to take a sort of small neighbourhood, and then I want to rescale and scale the metric. Just do a not even a well, it is a conformal change of metric, but it's a conformal change of metric with a constant. I multiply by the same scale by the same factor in each tangent space. Just scale the metric by it must be d to the minus 2. So I make d is small, so all distances are being. Maybe I mean d to the minus 1. So norm v goes to norm v over d. So the inner product gets scaled by d to the minus 2. And if you do that, curvature, sectional curvature goes to sectional curvature times d squared. And derivatives of the sectional curvature will, if I have d to the little k times k, that will go to k to the d to the 2 plus k. And so if you think of doing this and you know Wolpert's estimates, what you find is that after you've done this local rescaling, your curvature that was blowing up towards minus infinity is now staying negative and bounded. And your derivative of the curvature is going to stay bounded. So you end up looking locally at geometry after you've rescaled it that is just like negative curvature with uniform bounds on things. And then you, this is basically what we use in this paper, but we do it in a very complicated way. We calculate everything that could possibly be calculated. And I think all you've got to do is think of putting in a collection of transversals to your geodesic flow. You put in some disks, maybe make them look like disks, transverse to the geodesic flow, which should be, there's going to be an infinite number of them that accumulate towards the end of the world. But the idea is that after you've rescaled, if you look locally, you see a finite number at a sort of nice bounded distance. And when you look at the transitions between these disks provided by the flow, you're just looking at geodesic flow in negative curvature with bounds on everything, going from sort of one transversal to a nearby transversal to the geodesic flow. And so the geometry, so what's going on with the geodesic flow out in the dangerous parts is actually no worse than what we had last time. And so that's, I am convinced that this is the explanation for why we were able to write those papers. And so I hope to actually turn this into a full, full-fledged paper with actual sort of proofs. But this has to be the right heuristic. And you should keep that in mind before you launch into reading any details. And so I think that's a good point at which to stop. I think there is actually a simple explanation for why it was possible to do things for the Weil Petersson geodesic flow. So thank you.
Any questions? I want to know what was so special about the dimension of the dicomodal space being bigger than 4?
what is special is that once it's greater than or equal to 4, I can produce a closed geodesic in the surface that splits it into 2 sort of disjoint pieces. And then I can have something that and when that cutting geodesic becomes short, I have a piece over here with a very long, almost cusp, and another piece on the other side with a very long, almost cusp. And then what's going on looks more or less like a Teicl space for a surface over here with at least 1 puncture, and another Teicl space here with at least 1 puncture. So you've almost got the product of those 2 Teicl spaces. The geometry of the Weil Petersson metric looks closer and closer to that product geometry as this guy in the middle gets shorter and shorter. And so you cannot get that phenomenon when the Teicl space is 2-dimensional and there's just 1 geodesic describing everything. And you can always get it when you have more than 1 geodesic. That's the explanation.
So over here you described property of Weil Petersson geodesics that they give convex functions on the lengths of curves. Is that a characterizing function of
that is a question that I have asked. The experts did not tell me the answer. I think it's a nice question. My gut feeling is that the answer ought to be yes. Somehow, because you're not talking about just some geodesics, you're talking about all of them.
Right.
So you ought to be able to think of somehow very long, very complicated geodesics, and the requiring those convexity properties of the length functions along them, or to put a lot of constraints on what the metric could be. And somebody who has is better equipped to do that kind of thing than I am, I reckon we'd have a shot at proving that that property characterizes Weil Petersson. Or if it doesn't characterize Weil Petersson, it ought to characterize some class of metrics that's mighty close to Weil Petersson. And so I would...
Is there a different sort of geometric characterization of Weil Petersson geodesics? Like in the way that there is for Teicl geodesics?
The knowledge of Weil Petersson geodesics is distinctly limited. I did learn that there is one example, well, essentially one example of a Weil Petersson geodesic. I forget exactly what it is, but it's of the nature that if I have a surface, say something like that, and there's a reflection symmetry, if I look at the vector tangent to that, well, that circle in the middle has to be a geodesic, because if it wasn't, sort of if the geodesic tangent to the vector, the geodesic for vectors tangent to it was something else, after you reflect, you'd have 2 geodesics, and something would be badly wrong. And so it's a symmetry argument like that has allowed them to identify a Weil Petersson geodesic in one special case. That is the only known. Well, I think there might be, maybe there's a couple of situations in which you can make the same trick, but it's the same trick. And that is I believe, the total knowledge of what Weil Petersson geodesics actually look like. It's a rather mysterious subject.
Thanks.
Any other questions? So let's thank the speaker once again.